Welcome back to week 3 of the ma161 calculus. My name is Götz Pfeiffer and this video is about polynomials. A polynomial or a polynomial function is a function p of x which has the form p of x is an times x to the n plus an minus 1 x to the n minus 1 and so on plus a2 x squared plus a1x plus a0. Here n is a non-negative integer and the a numbers here, a0, a1 up to an, are so-called coefficients, which are any real numbers. Usually this is written in such a way that the first coefficient, the leading coefficient that goes with the highest power of n of x here, is not 0, and then we say that the polynomial p has degree n. N then is the highest power of x that occurs in the formula that describes the polynomial. Polynomials are nice in calculus terms, and we'll get to appreciate that as we go along. One of the first observations about polynomials, despite the fact that this formula is long, quite a mouthful, it's not problematic in any sense that has been mentioned before. Or to be specific, the domain of any polynomial is all of the real numbers. There's no danger of division by 0, or no danger that the formula given here produces something that's not a real number. So you can substitute any real number x into a polynomial and you get a meaningful value out of it. As an extreme example, a polynomial of degree 1 is the linear function that we considered in the previous videos. A function of the form p of x is ax plus b. That's this long expression which only extends, reading backwards, up to the coefficient a1, which serves as the slope in this linear function. Here's an example of a polynomial of degree 3, p of x given by the formula 2x to the 6. What did I say? Polynomial of degree 6. 2x to the 6 minus x to the 4 plus 2/5 x cubed minus square root of 2. And that's how they can look like, polynomials. Or in terms of graphs, here's a graph of a polynomial of degree 3. It comes here, goes up, goes down, goes up. Here's a polynomial of degree 4. Y is given by the formula x to the 4 minus 3x squared plus x. This graph comes from above, goes down, up, down again, and then goes off in that direction. And here's a polynomial of degree 5. This is the formula y is 3 over 10 x to the 5th minus 5 over 2x cubed plus 6x, and it has this shape. We will develop calculus tools that explain why these functions have these particular shapes and how we can be more specific about them. For the moment, this is just a first impression. The types of polynomials, apart from the linear functions, which occur most often probably are the quadratics and the cubic polynomials. Let's look at quadratics for a moment. Polynomials are used quite often to model quantities in a science setting, natural or social sciences, like Newton and apples. The distance d traveled by a falling object in terms of time is given by the formula d is 1/2 gt squared, where g stands for gravity. That's a formula involving a quadratic. A polynomial of degree 2 in general is called a quadratic polynomial, and it has the form p of x is ax squared plus bx plus c. The graph of a quadratic is a parabola, which is obtained by shifting the parabola y equals ax squared to the left, to the right, up or down, and the parabola opens upwards when the a is positive, and it opens downwards when the a is negative. Also, with a quadratic polynomial, there comes a quadratic equation. When you set the polynomial equal to 0, then we know that we can use the quadratic formula to find the zeros of the polynomial, to find the values of x, where p of x given by this formula becomes 0. Now, these are of interest in a number of ways, and the quadratic formula allows us to find them. If we found them, and let's say we call them capital A and capital B, then we can use the zeros of the quadratic to express the quadratic polynomial in factorized form as x minus a times x minus b times some constant k, which is needed to get the which is your a here, is it? The point being, using the quadratic formula to find the zeros of a quadratic polynomial allows us to write the quadratic, which here is given as a sum of things, in a new form as a product of things, which is useful in its own ways. Here's an example. Let's consider the quadratic polynomial p of x given by minus 2x squared plus 3x plus 2. The quadratic formula tells us that p of x evaluates to 0 if and only if x is quadratic minus 3 plus minus square root of 3 squared minus 4 ac, that's minus 2 times 2, divided by 2a, that's 2 minus 2's, which simplifies to this square root is this to be the square root of 25, so this simplifies to minus 3 plus minus 5 divided by minus 4, or evaluating the two possibilities, x is minus 1/2 or x equals 2. That's the two values of x which make p of x 0. Then, using this approach, we can write p of x as x minus 2, it's always minus the number that gives the 0, times x minus minus 1/2, which is x plus 1/2, times the minus 2, which is the little a coefficient in the given polynomial here. If you don't believe this, just multiply it out and see whether you get this form of the quadratic polynomial back. I bet you do. Here is the graph of this polynomial function. It has the little a coefficient here being minus 2. It's a parabola which opens downwards, and this graph crosses the x-axis at minus 1/2 and at 2. Just like we calculated here the zeros of the polynomial by using the quadratic formula. Of course, as you know, the quadratic formula doesn't always work out. Here we're extracting square roots. If the thing under the root happens to be a negative number, then the square root won't be a real number, and so the quadratic has no zeros. Or in other words, not every quadratic polynomial can be written in this form. P of x is k times x minus capital A, x minus capital B. But some can, and sometimes it's useful to have this factorized form, because as you see, the information it carries is where does the function become zero, where does the graph cross the x-axis, and also what is the little a coefficient that decides about the general shape and direction of the parabola, which is the graph of the function. Next up are the cubic functions, polynomials of degree 3. A polynomial of degree 3 is called a cubic function, and it has the general form p of x is ax cubed plus bx squared plus cx plus d for numbers a, b, c, d, and of course the a is not 0. Cubic functions do occur in science, in formulas. Volumes typically involve cubes. The volume of a cube is the cube of the side length, hence the name cubic. Or the volume of a sphere grows with the cube of its radius. The volume of a sphere as a function of the radius is v of r is 4/3 times pi r cubed. There are other more concrete scientific settings. For example, in analytical chemistry, there's a famous equation, the Charlow equation, which involves a cubic. Or in geophysics, Rayleigh waves, as they are produced, for example, by earthquakes, are governed by a cubic equation. Similar to what we've seen with the quadratics, cubic functions, cubic polynomials, can be represented in a factorized form. Well, some of them. Here the form is k times x minus capital A, x minus capital B, x minus capital C for numbers a, b, c, and k is not 0. And some cubic functions can be written in this form. Not every cubic function has this form, but it's as for the quadratics, it's a useful way to write this function, and that's illustrated in the following example, where we derive the formula for a cubic from its graph. So here we have a graph, and we're told that this graph is the graph of a cubic polynomial. What's its equation? What you can do with the graph is read off particular values, particular function values y at particular choices of x. And maybe the most interesting ones are the places where the graph crosses the x-axis. That's again the zeros here of the cubic polynomial, and here we find the zeros at -1, +1, and +2. And similar to what we did in the quadratic case, if we assume that this cubic function p of x has the form, has this factorized form, k times x minus a, x minus b, x minus c, then all we need to do is find the a, b, c, and k. And these values a, b, and c are the zeros of the polynomial. So these we can read off straight from the graph. There are in some order -1, 1 and 2. So we know straight away that p of x is k times x plus 1, x minus 1, x minus 2. The only remaining question is, what's the value of k? Now we can plug in another point that we read off the graph. I would try the y-intercept next, because that makes for easier calculations. And here this looks like the y-intercept is 1. P evaluated at 0 is 1. If we plug this into the equation as we have it already, substituting 0 for x, and then p of 0, the left-hand side here, by 1, we find that p of 0, which is 1, is the same as k times 1 substituting 0 for x, k times 1 times -1 times -2 comes to 2k in total, and p of 0 we know is 1, so 2k is 1. That makes k equal to 1/2. There we have it. Putting everything together, p of x now is 1/2 times the factors we found earlier, x plus 1, x minus 1, x minus 2, and if you multiply that out, you get a polynomial representation of this as half x cubed minus x squared minus half of x plus 1. That's it for the polynomials. The next video will be about power functions.